In this lesson, we're going to have a look at nuclear power. We're going to start by looking at the health hazards of ionizing radiation and something called background radiation. Then we're going to have a look at the mass energy equivalence. We're going to look at fusion, nuclear fusion, then nuclear fission. We're going to have a look at how nuclear power stations operate, and then we're going to revisit the mass energy equivalence thing with a bit of a more mathsy rigor a bit later on. Okay, let's get started. And we're better to start then with people, and all their weird and crazy wonderfulness. So people are an example of multicellular organisms. So things that are made up of loads of cells that work together to make an organism. So usually cells will work together to form organs. Those organs will cooperate together in an organ system. So for example, like your heart will cooperate with your blood vessels. And these systems all interact with each other. Now, the levels of complexity here are crazy. I mean, even just the structure of one cell is a pretty complex thing. And how those cells interact with each other, the metabolic pathways that govern how you as an organism function, are crazy complex. Like, here's what we think is the full set of metabolic pathways that a human cell will do. And like, just for context, if you study biology and you've looked at Krebs cycle, that's that little circle in the center. It's incredibly complex. And that complexity is governed by how the cells interact with each other and how they're controlled. This is down to the molecular level. And at the molecular level, all of your cells' interactions, both with itself and with other cells, are usually dictated by enzymes. But regardless of which molecules we're talking about, they're pretty fragile. So if they get damaged, the molecules that control your cells, if they get damaged, then nothing really works as it should and things start to get damaged. So if you think back to ionizing radiation, like our alpha, beta, gamma, X-rays, even free neutrons, if they start to interact with those molecules and start damage them by knocking off electrons and ionizing them, they can wreak havoc. So this damage to all your cells has symptoms at a larger scale that's quite easy to see. They range from like dehydration, vomiting, diarrhea, and acute radiation poisoning. You can also get severe burns, develop leukemia and other cancers. Even if people survive, the radiation can cause damage to their gonads, to their ovaries and testicles, meaning that any offspring they might have some genetic defects. For example, in the victims of Chernobyl, the survivors of Chernobyl, often their children and grandchildren had some pretty horrific genetic defects caused by the exposure to radiation. Of course, a big enough dose of radiation poisoning will simply kill you. For example, during immediately after the bombings in Hiroshima and Nagasaki, the atomic weapons, the end of World War II, many of the deaths weren't down to the fireball and the energy expelled, which would be horrific enough. Many of them were down to radiation poisoning in the days, weeks, months afterwards, and it's a pretty nasty way to go. A more recent example of acute radiation poisoning was this fellow here, Alexander Litvinenko. He was an ex-FSB operative, so he used to work for what used to be the KGB in Russia. He defected to the UK, but his ex-colleagues caught up with him. And it's widely believed that he was gotten to ingest some polonium-210, so they might have slipped into his food or a drink, which is an alpha emitter. So it's he ingested like a source of alpha radiation, and it killed him in a fairly horrible way. So these are very real dangers to ionizing radiation. Now that being said, and for all the grimness and the horror of victims of atomic weapons and radiation poisoning, be it in Chernobyl or the more deliberate case of Litvinenko, I mean, for all of that, life has adapted to a certain amount of radiation. It had to. So even though we talked about very artificial sources of radiation, they're not the only sources, and even they're not even the most significant. So there's a certain amount of background radiation. What this means is the radiation that's literally in the background all along. This is a diagram of how it breaks down by percentage. So for the most part, most of our background radiation comes from this radon gas. So this comes down to the rocks underneath us contain a certain amount of uranium. Now, that by itself is radioactive, which produces a certain amount of radiation. But when it decays, some of its decay products are themselves radioactive, including this radon gas. So it'll tend to accumulate kind of low down, so in basements and stuff. But even just going back to the rocks, so the materials we use to build things out of emit a certain amount of background radiation. The space cosmic rays are hitting us all the time with a certain amount of background radiation. Now that's all fine. It's not all fine. I mean, all radiation is damaging, but we can tolerate a certain amount of background radiation. I know that you guys are familiar with the idea of conserving mass and also the idea of conserving energy, so that mass can't be created or destroyed, energy can't be created or destroyed. It can only be converted from one form to another. But one kind of earth-shattering, um, perspective-shifting realization that Albert Einstein came up with. I mean, this guy is a mega genius. He was so smart. He's now kind of synonymous with being a genius. And even his most famous formula, E equals mc squared, not a lot of people really grasp the implications of it. Very few do. I doubt I do. Wide reaching implications for, like, light speed, quantum physics, but in particular this. So the idea that energy and mass are just different forms of one another, that energy can be converted into mass and mass can be converted into energy. Again, earth shattering, and it's worth just taking a moment to think about it, that energy and mass are just different versions of each other. So this E equals mc squared isn't just an equation, it's showing you numerically the values. So if you were to take a certain amount of mass and convert it into energy, how much would you get? And the key here is that because c here is the speed of light, 3 by 10 to the 8 meters per second, that's a really big number. So even if you convert a tiny amount of mass to energy, you're going to get a whole lot of energy. Okay, and we're going to revisit this with a more mathsy kind of vibe later on. But just to get it out there, that mass and energy are one and the same. They're just different versions of each other. Okay. Okay, I'm going to rein in the enthusiasm a bit, get a bit more self-disciplined. So let's look at one example of this energy mass conversion idea. So let's look at fusion, nuclear fusion. So again, let's start off with people, and us, we're quite wonderful. How do we stay alive? All right, well, for the most part, you're going to need food. So you're going to need some energy that you get in from your food. Where does the food come from? Well, the food comes from plants. It's either plants themselves or things that eat plants, if you're all carnivorous. So where do the plants get their energy? They get their energy from the sun, because plants are able to take the energy that the sun gives out and use it to rearrange organic molecules to form sugar, as in stored energy. Okay, so let's go back to the sun. The sun is able to produce such vast amount of energy because it's essentially a massive nuclear fusion reactor. So what is nuclear fusion? Well, nuclear fusion is when you fuse together two nuclei, two smaller nuclei to form a bigger one. And this will end up with a release of some energy. So there's going to be a loss of mass and a release of some energy. So let's look at a specific example. So let's go through an example of fusion. So you're all already familiar with a hydrogen atom, which is just one proton on its own, no neutrons. But there also exists different isotopes of hydrogen. And the one we're going to look at today is called deuterium, and it's a proton with one neutron. So it's a hydrogen atom with an extra neutron, with a neutron. So we write this as H with 2 for the mass number and 1 for the atomic number. Okay, so we're going to try and fuse two of these deuterium, two of these hydrogen 2 isotopes together. Now the problem is we're ignoring all the electrons here for now, we're just looking at the nuclei. And both nuclei are positively charged. So if we're trying to fuse them together, if we're trying to push them together, because they're both positively charged, they're going to repel against each other. So first thing we're going to do is we're going to need to really hammer these together. You're going to need a lot of kinetic energy to overcome that force of repulsion between the two positive nuclei. So really, to get them to that kind of speed, you're going to need to really heat them up, crazy heat, to about 10 to the 8 kelvins. So if you get them crazy hot, you can get them to fuse. So here we've slammed together two of these hydrogen nuclei, and we've got an isotope of helium. This combination of two deuterium atoms also ends up with one neutron being released. And crucially for what we're looking for today, there's also energy released. Now, these aren't normally written down on nuclear equations, but this is kind of the point what we're looking at today, the energy that's released. And it's usually released in the kinetic energy of the product, so how fast they're moving. Okay, so if you wanted to summarize in a nuclear equation, you've got your two deuterium nuclei. They fuse together to form an isotope of helium. There's also a neutron. And the neutron, whether that's there or not, depends on the particular fusion reaction. But the crucial thing here again is that energy is released. Here's another example with a normal hydrogen. I want to say normal, a H1 hydrogen atom with a deuterium, also giving you a helium nucleus with some energy released, but no neutron this time. We're going to look at how nuclear power stations work later on, but for now, just a quick note on fusion. If we're able to crack fusion as a source of power in a practical way on Earth, we would basically solve the energy crisis. Now, we're still quite a way away from that yet, because to get fusion working requires tremendous amounts of energy to initiate it, and you also need like a lot of mass. Now, the advantages would be that if we were to use hydrogen as a fuel source, we've got tons of hydrogen just locked into water molecules in the sea. There'd be very little radioactive waste, especially compared to nuclear fission, um, and we'd get an absolute shed load of energy from it. So it would be magnificent, but we're still a ways away from it yet. While we don't have the technology for nuclear fusion yet, we do have the technology to harness nuclear fission in power stations. Now, before we look at power stations themselves, we just need to understand how fission works. So in particular today, we're going to be looking at uranium. Now, uranium isn't the only type of radioactive material that undergoes nuclear fission. Plutonium does as well, but we're going to use uranium as our main kind of thrust. Okay, so uranium comes in three flavors. There's three main isotopes of uranium. But you can ignore the U-234 there on the left for now and just focus on the two on the right. So uranium-235, there's not very much of it. There's only about 0.7%, whereas uranium-238, that's what constitutes most of the uranium you find. About 99% is going to be U-238. Now, we're going to be mostly looking at U-235, the kind of rare one, and how it works. Okay, so if you took a nucleus of uranium-235 and bombarded it with neutrons, that's going to cause it to split, to undergo fission. So because it can split, we say that this is fissile. Okay, so we bombard our uranium-235 with a neutron. Now, we're saying bombardment kind of implies that there's tons of them, but only one's going to be accepted in. So one neutron gets added to the uranium-235 nucleus. This causes it to split, and it's going to split into two roughly equal-sized nuclei that come from it. Now, the exact breakdown of it doesn't matter too much, but for our example here, we're going to say it's breaking down into barium and krypton. But really what we're focused on here are the neutrons that are also released here. So all of these products are kind of going to go flying away from each other at tremendous speeds. And this is the key again, energy is being released. So they're all going their separate ways under a great deal of energy. So to summarize it, uranium-235 nucleus bombarded with a neutron splits up into some fissile products, into some products. So krypton and barium in our example. And they're all going to go in their own separate ways along with the two neutrons. Okay, so that's kind of how nuclear fission would happen with one atom. So one atom of uranium and how it splits up. But in reality, that one atom is going to be part of many, many billions. So to see what happens now, we're going to model it with using these kind of orange rectangles to be uranium-235 nuclei, and we're going to see what happens. So remember that because uranium can split, we say that it is fissile because it can undergo fission. Okay, so let's say we've got our sample of uranium-235 and we bombard it with some neutrons. Now I know we've been using blue for neutrons so far, but I ran out of colours. So say a neutron comes along, hits one of these uranium nuclei, that's going to split by nuclear fission into the two fissile products, the barium krypton for example, but we don't really care too much about which particular products were formed. Instead, we're more interested in the two neutrons that are also released. Get off. Problems are working on Play-Doh. Okay, so you can probably figure out that straight away in a sample that was, let's say, this size, everything is exaggerated here. Obviously, there's millions and billions of actual molecules there, but let's say that our atoms there. Let's say this is the case. It's pretty obvious to say that both these neutrons would most likely just escape, fly away, no problem. But let's say that they do manage to hit two other uranium nuclei. They're in turn going to split. They're going to split, and they're each going to release two more neutrons. So every time this happens, if those two neutrons kept hitting, bombarding into other uranium-235 nuclei, they're going to make them split. And this is going to keep going on and on and on. More neutrons, more splitting, and you've got a chain reaction. And in fact, in this case, because each of the two were hitting a uranium nucleus, you'd have a kind of an uncontrolled chain reaction. It'll keep getting bigger and bigger and bigger. So in a relatively small sample of uranium-235, those neutrons that get emitted will just kind of go flying off and they'll escape the sample without really doing much. But in a larger sample, one that is above what we call the critical size, meaning that there's enough of it, those neutrons won't escape without hitting other nuclei. And then things get a little bit more interesting, which brings us neatly on to nuclear power stations and how they work. So let's have a look at how a uranium-based nuclear fission station works. All right, to get our heads around this, let's revisit what uranium is. So most of the isotopes of uranium you're going to find are 99% of them are going to be this uranium-238, which for our purposes isn't particularly useful. It's the U-235 we're looking for, but remember that's only 0.7% of the isotopes. Okay, so let's compare the two. So the two that we're really interested in are U-235 and U-237. So when they get bombarded by neutrons, how they're going to react and how they're going to behave depends on the speed of the neutrons. So there's two types. They can either be moving fast or they can be moving slow. Now all this is relative. They're all still moving pretty fast. But let's broadly categorize them as fast-moving neutrons and slow-moving neutrons. So with uranium-235, if it's hit by a fast-moving neutron, it will undergo fission. And also if it's hit by a slow-moving neutron, it'll undergo fission. But the key here is it's much more likely to split, to undergo fission, if it's hit by a slower neutron. Whereas uranium-238, if it's hit by a fast neutron, it will absorb it, but nothing else will really happen, it won't split. And if it's hit by a slow-moving neutron, nothing really happens, it doesn't really absorb them. And that's going to be crucial for how we get our sample of uranium to actually work. So again, let's scale it up to imagine how this is going to work in an actual sample of uranium, which is going to contain many billions of atoms. So let's say we've got a sample of natural uranium. 99% is this U-238, which we're going to represent by these little green squares. And some of them are going to be uranium-235, which we represent by these little orange squares. Okay, so let's say that this particular atom of uranium-235 manages to undergo fission and emits two neutrons that are going to be moving. Okay, well if they're moving at a fast speed, they're going to be very quickly absorbed by the uranium-238 that's nearby. And that means that's kind of the end of the reaction. Nothing else really happens. But if we're able to somehow slow down these neutrons, then the U-238s aren't going to absorb them. So those neutrons will be free to keep moving, and eventually they'll meet the other uranium-235 atoms and cause them to undergo fission. So the key here is we're going to need some way to slow them down. So this is going to give us a chain reaction. Now again, we're going to want to make sure this is controlled, because an uncontrolled nuclear reaction is what happened in Hiroshima and Nagasaki. We want it to be controlled and regulated. Okay, so let's have a look at it. So the key to getting this nuclear power station to work for us is we're going to need the neutrons that are emitted from fission to be moving at the right speeds. We need them to be moderated so they can hit the other uranium-235s and cause them to undergo fission. But we also want to control the rate of the reaction so we don't have an uncontrolled nuclear reaction. Okay, so let's start with the fuel rods. So these are literally just rods of uranium. And because they're natural uranium, they're going to be a mix of uranium-235 and 238. Sometimes they can be enriched by adding a little bit of extra U-235 to the mix. That's what enriched uranium is. But generally it's going to be mostly U-238. Okay, so we have our fuel rods. Now we're going to use what's called a moderator. So a moderator is a material like graphite or deuterium. And what it does is it slows down the neutrons. It doesn't absorb them, but it slows them down. You might know the word moderator from the moderator of a debate, whose job is to keep things kind of sane and calm and measured. Well, this moderator, it doesn't really do that. This is more like someone that wants more chaos, wants more fission to happen. So the moderator in this case is slowing down the neutrons to allow us to have more fission. Okay, so we're going to need some way to kind of stop this from getting out of hand, because if that was just the case, you get a pretty quick uncontrolled nuclear reaction. So instead we've also got these control rods, which are made usually of cadmium or steel. And they're made of material that is going to absorb neutrons harmlessly, just absorb them and stop the reaction from happening. So these control rods can kind of be wrapped around the fuel rods, and you can control how much of the fuel rods are shielded or not by these control rods. So if you drop the control rods down onto the fuel rods, you can completely stop the reaction. So for this reason, these rods are normally placed above the reactor, so that if there's some sort of accident or some sort of problem, they'll drop down, shielding the fuel rods, absorbing all the neutrons and stopping the reaction. But if you want a little bit going on, which is the whole point of the power station, you want some of this reaction to happen, you can expose some of the fuel rods. So by controlling how much of the control rods cover the fuel rods, you can control the rate of the reaction. Okay, so how do we harness this fission? So remember that the fission is going to be causing massive amounts of heat to be emitted. So we need to harness that heat, which is the core of how all power stations work. They usually just harness the heat and cause it to make something move, which we know is going to be connected to a generator. Okay, so we're going to harness this heat by using some coolant. Now the name's a little bit misleading here. It's not to cool things down, it's to carry the heat. So you carry the heat from the coolant, and the coolant runs through a series of pipes, and these pipes are in close proximity to another source of water. They don't actually mix. The water in the reactor doesn't mix with the water that it's heating, but it does heat this water that runs nearby, which is connected to a turbine, which can then be used to generate electricity. And of course, the reactor itself is encased in a lot of shielding to protect, people from radiation. Okay, I did say that we're going to look at the mass energy equivalence calculations, but because this video is already at like 21 minutes and YouTube's going to have a conniption, I'm going to update that as a second separate video and we're going to work through some of the problems together. Okay,